So, oops. Now again, something new. Now it gives an echo. No. Okay. So, okay. So, was ist denn jetzt? Okay. So let me first say who is the organizer of this. That is the Collaborative Research Center 876, and that is about big data and small devices. Big data require novel algorithms, for instance, on data streams, for instance, in many ways of having distributed processing. It is the Internet of Things that produces real-time streaming data, and this is a number of data that is increasing constantly. And it is executing the learned models on embedded systems, and that requires fast inference. So it is, we have the data, we have the learned models, and we have an execution on small devices that are embedded almost everywhere, we could say. So that was the main idea why we started in 2010 with resource-constrained data analysis, because we said on either, it could be that there are just really big data, and then even a regular computer is a small device. Or it could be that we have a stream of data where each data item is rather small, but it is also a very small device, for instance, one with zero energy use. What is a collaborative research center? Maybe you do not know that this is the most challenging research funding in Germany. It allows you to propose a novel idea, and if you convince colleagues to share their work with you on this topic, then you might get a grant that is for 3 phases, each 4 years. And if you are very successful, then you get even the 12 years. And the nice thing is we got this. We are now in the last year of the 12 years of this collaborative research center, which I proposed together with Peter Marwedel, who is here. I'm very happy that you are here, because we too in 2008 decided that we wanted to make such a research center, and we found excellent colleagues sharing our views and really contributing a lot to it. So it is always 13 projects, including a graduate school, and about 50 PhD students. That's the regular size of a collaborative research. So, but this is just about what a collaborative research center is. And now let me talk about the about my talk, about our content, that we are, what is our research about. That is, the first point I want to make is machine learning provides us with insights in other sciences. So that is something which is really fascinating. It can come in many flavors. I started personally with cognitive aspects of machine learning. So what is learning in humans? What is learning in machines? How can machine learning models help you understand how children acquire concepts and so on? That was something which started my interest. How do we learn language and so on? So this is the one insight that you can gain, and the other insight is you can gain it in things like, for instance, astroparticle physics. And that is what I will be talking about. Insight into machine learning itself is also very important, because otherwise, without a good theory, you cannot make machine learning efficient and reliable. And then machine learning is automating processes. And for a computer scientist, it is really exciting how much automatization we have observed with machine learning. And I gave you some example of that as well. So a particular Dortmund approach to AI and machine learning is to not only look at the knowledge and data and make hybrid systems, we all know that, many people do that, but we also take into account the architecture of the executing engine. So we really, even when we gather the data, even when we do our algorithmic models, we look into the execution, into the hardware that is using it. And we did that from the beginning on, although this hardware-related aspect of machine learning internationally was recognized many years later. So machine learning provides us with insights into other sciences. And there, something which in the SFB has been done for some years is the inspection of genetic data. And then, of course, the challenge is how can we determine early on whether a therapy will be successful or not? And that was particularly exciting if we look at children. That is, the neuroblastoma is a cancer that is with young boys, and young means 1 year old babies, most often male ones. And there, this cancer is, of course, very difficult to do a therapy on, because with this little body, how much chemical things can you put in without destroying this body? So it is very challenging. And the funny thing is that there exist children that even without therapy survive and become healthy again. And now the dream was to identify the genetic constellation such that you can say this child safely can refuse to get any chemical therapy. And the outcome is we did not succeed in that. I personally just found one genetic code that, is the contrary, made it very likely that the child will not survive. That was not the one I was looking for. So you never know what you get in the data. But it is going on. And what you see is a lot of publications, and it even made it to Nature Genetics. And there are my nice colleagues, Alexander Schramm from the clinic in Essen, and Sven Rahman. Indirectly, he is involved here by a talk. And then, of course, Jens Rahnenführer, who is hidden somewhere in the et alii somewhere. So the lecture about this topic, more or less, is today by Johannes Köster. Okay, and then another field of science is astrophysics, where we are fascinated in events that occurred some 1,000 years ago, some billion light years away. And there are methods of measurement where you can actually measure signs that help you infer that such an event has happened. And also there we have been with SFB in the science that was on the neutrino experiments of the ice cube. What you see here are the optical elements of the ice cube experiment. There is a large collaboration of IceCube, and that is really looking at our contribution, discussing it, all the 200 scientists, until you get a publication with a full collaboration. And we managed to do that 2 times. So the last one is on a convolutional neural network-based cascade reconstruction for the IceCube Neutrino Observatory. And so that's from last year. But there are many other things, and there is a lecture by Tim Ruhe today, where you can move into that. Now, I give you, on the example of astroparticle physics, I show you what this all means all the time, because it's always the same. What you have is you have a scientific question. So it might also be, how do children learn language? but it can also be how is dark matter occurring or isn't it at all. And then you have a data understanding, then you have data preparation, modeling, evaluation, and then in the end, you get an insight, maybe the one you looked for, or maybe another one. You never know. And I think this leads to the next question. And then you go the circle again and again. And here, what I want to show is machine learning is an instrument of science, and there are senses of science. And in astrophysics, it's the ice cube collaboration and the Cherenkov telescope. CT is for Cherenkov's telescope. And machine learning is also a science in its own right. Don't forget that. It is not just a tool where you click. So ice cube, what is it? What you see there is a detector, and that is a kilometer-long holes in the ice of the South Pole. And in these holes in the ice, it must be ice because it's clear material. Therefore, the dust layer is here shown because then it's not clear, and then you do not get good measurements. And then you have these optical devices, and what you can then do is a reconstruction of events, and you can have cascade events so that the particle is going all through the Earth. So it comes from outer space, then comes to the Earth, then from the north to the south goes down to the Earth, then goes through this ice, and then hits some of these electrical things. And then you must follow the trace of this particular particle by the lights in these optoelectronic thingies. And then you estimate some particular directions, so that you have this direction vector, and then you have particular angles, and by then you can compute the direction and project that to outer space and then see where this particle comes from. And what you need to know is most particles that you see are without any relevance because they are just going around. And only these neutrinos are the ones that we want to look for. And there is only one neutrino in 10,000 other particle things. So, okay. So what did we do? What you have is this nice work of Mirko Hünefeld, where you see this deep network with the convolution layers, and then you have these layers that in the end directly claim how much energy has this particle and where it is from. But at the same time, you also have this other last phase where you calculate uncertainty, because it is very important that you know how certain is the prediction or the classification that your neural network computes. And so methodologically, it is an interesting approach. So for each label, it is a neutrino, it is just some particle. These are the labels. You find an optimal loss functions according to the importance. And at higher energies, you can find by the convolutions a better angle reconstruction of the particle, superior to the ones we had before. And the convolutional neural network model takes less than 24 milliseconds for most of the events. And that is, of course, very important, because what you also have is these multi-messenger impulses, so that if you measure, here could be something interested from there, then you ask all the other senses of astrophysics around the world whether they measure there's something interesting as well. Okay, so faster than light. This is something very important. Can apparent superluminal neutrino speeds be explained as a quantum weak measurement? That was a nice paper, and its abstract is probably not. And the reason why there was a faster than light neutrino was a loose cable in the CERN. So what you see, why I give that for two reasons. The one is that I like this humor that physics have in their publications. And the other is that actually you have these machines that take the signals, and you have the machines that analyze and the machines that execute. And there are so many ways where things can go wrong, right? Okay, so that's the one thing. But actually, what is faster than light is the Cherenkov light in particular medium. So it must be clear ice, for instance, like an ice cube. There are Japanese ones that take clear water, and there is also the clean air. And that is the Cherenkov telescope on the island of La Palma, where you find clear air and no light diffusion, and therefore you can recognize there the Cherenkov light from particles. And there we are interested not in the neutrino, but in the gamma rays, because the gamma rays also go straight and you can follow their trace and infer where they come from. Okay, so the medium can be water, ice, or air. And here is a kind of a picture of a Cherenkov telescope. The Cherenkov telescope gets the air shower from the atmosphere, and then it hits the telescope, and that has all these hexagons. And then if it hits a cell there, you see the light, and this is taken as a picture by a camera that is looking at this. So then you get these camera samples, and they are over time, and then you see hopefully that there is a gamma ray, or you see that there is just something else, and you have to classify which is what. And okay, so the model of the distribution of gamma rays separate gamma rays from other rays. And what you see here with the outlier detection is something which we did where on the fly by submodular functions, we could find the most, sample the most interesting pictures. And Jens, who you know, classified these most interesting pictures and really found that these are specific and prototypical pictures for certain situations. And so in a way, this is a data summary, which you can understand from the tons, the terabytes of data. You get just these, and these are prototypical and nice. And that is, of course, an algorithmic challenge as well, because you have to do then these very fast algorithms. Now, coming to another experiment that we did with the FACT tool, and that was a telescope. And that was, we first had a process in the regular way of machine learning, feature extraction, signal separation, energy estimation, and we did that in extra steps. So we had a long pipeline of data stream algorithms that worked together and developed very good results, by the way. It was excellent. But then we tried out the claim of deep learning, that deep learning can do all the representation learning in its own right. And we said, okay, we want to have so-called end-to-end learning. The physics people do not call it end-to-end because they think of the telescope engineering and all the things they had to do before. But regarding the data, it is end-to-end learning. And what we did is we had the input a little bit turned. The picture is a little bit turned so that we do not have to change the input to the convolutional neural network. And then we had to do a lot of experiments in finding the right deep learning architecture. This is cumbersome. And then we found a simple visual GG architecture, which is sketched here. And that was really delivering very good results. So the performance on simulation data, there we had the random forest, that was the standard before. Then we had the convolutional neural network, a small and a large one. And then we binarized the convolutional neural network to make it more efficient, to a binarized neural network. And that is very good because it doesn't take much energy and it is very fast. And it even, well, the large CNN outperforms the standard random forest, but the BNN also outperformed the random forest. So you have either the full convolutional network that is taking a lot of energy, or you have the binary network. In both cases, you are better than before, and you really do end-to-end learning in the way that machine learners call end-to-end. And then you can do not only a test on the test data, as usual, but you could say, you know, this Crab Nebula data, you know that there is this Krebsnebel Crab Nebula. You know where it is. It was, I think it was detected by a Chinese astronomer in 1100 after Christ's birth. So it's well known that there is this Crab Nebula. And then you turn the telescope into that direction, and you turn it into other directions. And then you test whether your algorithm really detects much more gamma rays in the direction of the Crab Nebula than in the other directions, right? And in this way, you test it, and actually the results are excellent, because the significance of rejecting the null hypothesis is here expressed by the standard deviation. And there is a particular metric for gamma, which are the good ones, and hadron, which are the ones you don't want to see, classifiers. And there, this metric is such that the larger value is always the better value. And there you see that actually with this, you get excellent results, even on the real case. Okay, so that was for the insight that you can gain in other sciences. Of course, there's much more in machine learning, but this is just a short introduction to all the interesting questions that there might be. But there is also insight into machine learning itself in order to make it efficient and reliable. And we should never forget that machine learning is a science in its own right. It is not just applications. It is a science, and you have to study it, and you cannot learn it in 50 minutes. So insights into machine learning, making it efficient and reliable. There, an example which I show here is a list of proofs of properties of probabilistic graphical models. And you see the formula that expresses probabilistic graphical models, or in general exponential families. And this formula needs to be realized by algorithms, and these algorithms need to be executed on particular hardware. So it's a long way from the formula to the particular thing. And then comes with a, actually, when you leave mathematics and you really do an action, then you use energy yourself. So the machine learning uses energy. And therefore, we are looking for algorithms that are still reliable, but use less memory, less communication, less computing capacity, and therefore less energy. So there is an example here that was done by Nico Piatkowski on integer. So we have just seen binary neural networks. And what Nico Piatkowski did was he invented integer computing for probable graphical models. And that is our approach of triangular AI, knowledge, data, and architecture again. Okay, so if you have the resource constraint energy, Max Welling said at the ICML 2018, the next battleground in AI might well be a race for the most energy efficient combination of hardware and algorithms. So in 2018, actually then our claim that we have to include hardware considerations into machine learning research was really announced at the leading conference. And what you will hear tomorrow is a talk of Wei-Luc and Chigu, a lecture on deep learning on FPGAs, which are computing architectures that use a lot less energy than others. But they are also, I mean, difficult to understand. We are used and educated in von Neumann architectures. And now there is something new and we have to learn something new, okay? And then there will be a talk by Andres Gomez on zero power learning on Wednesday. So what we have to do is we have to design algorithms that save resources. We have to design algorithms for particular hardware that saves energy. We have to move beyond the von Neumann architecture, for instance, in memory architectures, as Jiajia Chen is doing a lot of research on memory. And we have to do design model execution that saves resources. That is, we not only design learning a model, but we also design executing a model. And there's a lot of fast inference work going on here. And here is the example. This is work by Sebastian Buschjäger, where you read in a model. It might be a linear model, a quadratic model, a decision tree, a neural network, an ensemble of learned models. And then you optimize the model, for instance, by weight clustering, by ensemble pruning, by node swapping. And then you choose a back end. And then you combine templates and execute it on a particular hardware. So this fast inference optimization of models for execution is of course very important, because then you can optimize the implementation for a given hardware, and you can do memory accuracy trade-off. And with that automatization, I want to give the view of machine learning as being something which is just automatizing computer science. And this is a good example of it. Yeah, this is what you see. It is an abstraction and then it is automized. Okay, and then of course everybody asks for interpretability. And there I found a very nice spot. There is always an easy solution to every human problem, so we can easily understand it. Neat, plausible, and wrong. And that is to say again, you cannot explain machine learning in 15 minutes and then everybody understands it. No, you have to study 4 years and then you can understand it. Yeah, that's it. And in these 4 years, of course, there's a lot of regular computer science that you need to study, and therefore it is an add-on, what we do in machine learning. So it is complex, and understanding it requires scientific education. And there are global and local models, which makes it very difficult. And here, what you see is, you have here an example of the, in 2006, Stefan Rüping was my PhD student, and he had a thesis on interpretability, and that was about the support vector machine. And there what he discovered is you can find a global model, a nice hyperplane, very easy to explain by the support vector machine, and then there are some nasty local models. There are some exceptional spaces. There are things that are not as well. And then you take there another model, so that you have global models and local models and how to combine them and so on. It's a whole thesis. So that was our approach to understandability and interpretability. Robustness is another thing. Small changes of the data should have only small changes on the model and the model performance. And we know that this is not always the case. Not all our models are robust. So we are fighting overfitting. And our standard models, we have very good methods that have been developed in statistics. But for other models, it is not yet really solved. There are adversarial attacks. There are perturbations of perceived objects. And this is one of the famous examples whereby just putting some stripes in black and white on a traffic sign, it was no longer recognized. Although we, as humans, we easily see that it is a stop sign. But the computer could no longer realize that. So it is a small change, and it really changed the classification. So this is something we have to fight. And how can we fight that? Well, on the one hand, our models are regularized. That is well known, but still for particular models, a matter of research. And then we need to do proofs of robustness. We have to prove how robust is my model. Okay, so then machine learning is automatizing processes, even its own ones. And there I want to show you some things, for instance, this zoo. This is the zoo which you need to have at hand if you are working in machine learning. And why do we have so many tools and not just Python? Why is that so? It is because we are building upon all the software developments that have been developed already. And then we build something on top of that, and then again on top of that, and then again on top of that. And my nice experience is, since I am in machine learning now since more than 35 years, I have experienced all these stairs. First, we were programming by hand on a machine. And then we were programming the programs that we had programmed, and so on, and so on, and so on. And nowadays, we are much further, and we have a lot of tools. And we have even more than the tools. We have these libraries that we can use. We have the GitHub repository with all the programs we can use. And what I like very much is papers with code, where you have papers and you have the code with them. And then you can look at the relation between the words in the paper and the code. And you can also, yeah, I will come to that in a minute. But before, let me say that these tools are also dangerous. Because many people then think, as a scikit-learn in 3 hours, full course, no, I can do it. I don't need to understand anything about data, about statistics, about mathematics, about algorithmics, about complexity theory. I don't need to know anything. I just can do it in 3 hours. And then they are very much disappointed. People doing that will always be disappointed. Okay, so that is here an example. Tools for validation can be used for further validation. That's my personal interest currently, and therefore we are looking for papers with code that can be used for automatic setup of experiments, so that we really do a setup of the experiments automatically. And then also, what is currently done by Gernot Schmitz in my lab, archive papers are search for proofs. So what we want to build up is a database of papers with proofs. And then we want to classify the proofs by the type of learning, by the properties that are proven, and so on. And then we want to generate experiments that test the proof properties for a given implementation. So you see that I'm looking much more into the future of what we can further do in automation on top of this paper with code website, which I recommend here. So the documentation of processes is actually a problem. What you see here is the big models. I mean, they have the pre-training, then they have the fine-tuning, and it is with 175 billion parameters. GPT-3 is not the largest one for language modeling. And the bidirectional encoder representation from the transformers, the BERT model shown there with 110 million parameters. It takes 12 kilowatt hours per training a BERT, and this is a situation which is unsatisfactory because we do not understand the model and it takes too much energy. So we have to do something about it. What then was decided in the companies, Google, IBM, and so on, that was they describe models and data. That's what they do by hand. Really, they have checklists by hand. I looked at it. It's true. It's a checklist by hand, and then whoop, that's what they do. And I mean, this is really the opposite of what I said. Machine learning is about optimization. This cannot be what we really want to stick with, and therefore we are working on care labels that do it automatically, and for all the levels of methods, for the formula, for the algorithm, and for the implementation. And the good thing about these care labels is that they are understandable at one glance. And they are understandable not in the way that you understand what the algorithm does, because you cannot without studying. But I do not understand my refrigerator either. And I even do not want to understand my refrigerator. I want to see a AAA that it doesn't use so much energy, and then it's fine. So that's what we did. We had a methods name, and then we have on the one hand the theoretical properties, and these are tested by automatically generated tests. And then we have on the execution environment, where for each platform you again do some tests how the model works on that platform. And then this is what you really have to do, and that is where the future of machine learning theory and practice is, that you have the theory with all the proofs, you have the implementation of the model, and then you have benchmark data that are tailored for the particular features that you want to prove. And then you have the certification suite that extracts the experiments that you have to run and then interprets the results of all these 1,000 runs of your algorithms, and then gives out this, outputs this nice certificate. Okay, now I go over that. I just show you two examples. The one is for this probabilistic graphical models, where you have two different algorithms into different implementations. So the algorithms are with a junction tree or with a loopy belief propagation. And the execution environments are a CPU platform or a GPU platform of a certain type. It's all described there. And then you give the labels: expressivity, usability, reliability, runtime, memory usage. And you see that these both implementations have very different profiles. So for a user, it is easy to decide which one he or she wants. Yeah, because you see the profile and you have your own needs, and then you say, runtime is not what I have any restrictions, so I take the junction tree, or you say runtime must be faster, then you take the loopy belief propagation. Of course, all this is based on theory. Then with deep neural networks, you don't have the theory. So you have to do something else. And what you do there is you use all these libraries of perturbations, and then you test your implemented model on all these perturbations. And we had here an example where we had AlexNet, ResNet, MobileNet, and VGG. And we tested them on very different things that we found in GitHub with all these robustness tests from all these groups, many, and then we measured things with a model, and then we had task-specific perturbations, corruptions at various levels using ImageNet data, and then we had the attacks created by Clever Hans. You know that probably. Very good library by the Berlin group started and then internationally enhanced and so on. And what you see there is, look at all these values. What you see is a picture that you can turn into a care label. And then you see that MobileNet and ResNet have very different profiles. And again, you have these two models and you have the two execution platforms where you measure it, and then model selection becomes easy. So what I have shown you is that machine learning provides us with insight in other sciences, and insights in machine learning makes it efficient and reliable. And you have seen that machine learning is automatizing processes. And this all illustrates our triangular AI approach that we have here in Dortmund. And this is also the approach of one of the 4 German centers. There are 4 German centers for machine learning starting this year, and one of them is in Dortmund. It's called the Lamar Institute for Machine Learning and Artificial Intelligence. It is named after the famous Hedy Lamar, who actually was working on hardware design, and therefore we strengthen by this that we are combining machine learning with hardware. Okay, so this is my introduction, and now we come to you, to the summer school, and I'm very happy that we have 71 participants in presence and many more in remote participation, 254. And if you look at the country distribution, then you have a good guess that among the ones from remote, the Korean could be the ones, or is there a Korean also here in presence? What a pity. Would be nice. Would be nice to have you also here in presence. And then if you look at the distribution of lecturers there, the distribution is quite different, of course, but also there we are quite international, and there are just 8 from our collaborative research center. And then you know what you can expect is lectures about cutting edge machine learning. I think that the Students' Corner might be very interesting for you, where you discuss and present your work and get nice questions by others. Then the hackathon is something special, because in Dortmund, the ESA's Institute is developing a virus detection that does not need to freeze the virus before extract it, but that you only spit on something, and then this virus detection gives a picture, and this picture has to be classified. There is a virus, there is no virus, and then which virus, and so on. So you can do it your own. These hackathons in former summer schools have always been a lot of fun. And then there is a banquet at the Art Nouveau coal mine, which is no longer mining coal, but offers you a nice banquet. So I hope that you'll enjoy it, and I want to thank the students, and in particular, of course, Jens Buss, who did really the job of organizing this. Okay, that's it.